Good morning, students. This is K. Lakshmi, Assistant Professor in the Department Tripoli, Chevrolet Engineering College, Lecturer 37, Unit 3, Magnetic Force. Topic: Magnetic Force on a current element. In this session, we discuss about the torque acting on a dipole. Before we discussing about, once we repeat the what is a Lorentz magnetic force and magnetic force acting on a current element, like that. Now, let us discuss about the Lorentz magnetic force. A current carrying conductor placed in a magnetic field, it experiences a force. So this is the figure represents the how the magnetic force is developed by a moving of a charge in a magnetic field. This is a charge Q moving with a velocity v. So due to movement of a charge, a current is developed. Now the direction of the current and the velocity are in the same direction. Now this moving charge placed in a magnetic field, this is the direction of the magnetic field. Due to that, this charge experience a force that is called Lorentz magnetic force or simply magnetic force. The expression for the Lorentz magnetic force is Fm is equal to Q V bar cross B bar. Or it is also expressed as here V cross B is like a cross B. So the formula for A cross B is AB sine theta. Like the same way, V cross B is equal to VB sine theta. So here the n cap means it is a vector, unit vector representation. Now here Q is the charge of the particle and V is the velocity of the charge. B is the magnetic field. Here the theta is the angle between velocity and to the magnetic field. So basing on this expression, what are the special cases are occurring? Let us discuss that. So these are the special cases. So the first one is if the charge is at rest, that means velocity is equal to 0. So by substituting the velocity is equal to 0 in this expression, the magnetic force value becomes to 0. That means when the charge is at rest or a stationary charge placed in a magnetic field does not experience any force. So that is the one of the case. If in case theta, that is the angle between velocity and to the magnetic field, maybe 0 or 180 degrees. That means if this theta angle is 0 means the charge move parallel to the applied magnetic field or it may be anti-parallel to the direction of magnetic field. Whatever that means irrespective of direction of velocity and magnetic field, the magnetic force value becomes to 0. Why? Because as we substitute theta is equal to 0 or 180 in this expression, sine 0 value is 0. So automatically the magnetic force value becomes to 0. In the similar manner, sine 180 value is also 0. So the magnetic force value becomes to 0. Okay, it is clear. So at theta value 0 or 180, the magnetic force experienced by a charge is 0. Now the last case is theta is equal to 90. That means the angle between velocity and to the magnetic field or in a perpendicular manner. then the exerted force on the particle is represented as Fm is equal to QVP. Why? Because as we substitute theta value 90 in this expression, sin theta value 90, sin 90 is 1. So Fm is equal to QVP. That means this force is maximum. So the suffix means the maximum force exerted by the moving particle when the direction of velocity and magnetic field are in a perpendicular manner. So these are the special cases we have to discuss in a Lorentz magnetic force. So in a velocity is equal to 0, then that means when the particle is at rest, the magnetic force is 0, or the angle between velocity and magnetic field is 0 or 180, then the magnetic force is 0. If the theta value is 90, then the magnetic force experienced by the particle is very maximum value that will be equal to QVP. Okay, now the next concept is force on a current carrying conductor in a uniform magnetic field. So this is the figure, and these lines are represents the magnetic field direction. So this is a cylindrical conductor. Now the area of the cylinder is A and the length of the cylinder is L. Now a current I is passed through it. So let us assume an electron experiences a force. So the force experienced an electron placed in a magnetic field. That means here the charge is moved with some velocity and now it is placed in a magnetic field. As we already discussed in Lorentz magnetic force, the same magnetic force is developed here. So this magnetic force is expressed as F is equal to minus E Vd cross B. So this is a comparable expression with magnetic force. Now compare with the magnetic force. F is equal to Q V cross B. Q means a charge. Here the charge of the particle we have to taken is electron. Now the charge of the electron is E and it is having a negative charge. So it is represented as a minus E. Now as compared with the magnetic force here, in place of V, there is a value of Vd. So what is Vd? Vd is called drift velocity. Whenever a particle moves with a velocity, that means electron moves with some velocity, its velocity is expressed in terms of drift velocity. So this is the expression we have to derive from magnetic force, that is F is equal to Q V cross B. Whenever this is the expression of the electron experienced force, that is F is equal to minus E Vd cross B. Let us assume small n be the number of density of electrons. That means here the infinite number of electrons are there. So the number of density of the electron, let us assume small n, and the area of the cross section of this cylinder is taken as capital A. And let us assume a smallest length. When you observe that here the green color DL, this is the smallest length. Now the number of electrons present in this smallest length, that means current element, is taken as N into A into DL. So this is the very important point. Now, the force experienced by the electron in this smallest length. So whatever we have to take in here, the smallest length is DL, then automatically the force experienced by the electron in this small DL length is represented by dF bar. So dF bar is equal to NA minus E Vd cross B bar. So which is equal to minus NE A Vd. So here N E A Vd or N is the charge density of the electron, and E is the charge of the electron, and Vd is called drift velocity. So dF is equal to minus NEAVD into dl cross B bar. So just to write we have to shift the dl into bracket. Now the value of NEAVD is equivalent to current. How we have to write here NEAVD as a I. So we know definition of current density. J is equal to I by A. From this, I is equal to J into area. J is called current density. Now the expression of current density in terms of drift velocity is written with the help of in classical mechanics, that is NEVD, and as it is the area is right here. So the expression for I, once again I repeat, J is called current density. This is current per unit area. From this expression, current is equal to J into area. So J is current density. So in classical mechanics, according to classical mechanics, J current density is expressed in terms of NEVD, and as it is area. So the current NEAVD is equal to current. And the negative sign here represents the direction of DL is opposite to that of VD. When you observe this figure, so this is the direction of DL, and this is the direction of velocity. So the direction of DL is opposite to VD. So automatically DF we can easily write as I dl cross B bar. Now the entire force experienced by the length L is obtained by integrating this equation on both sides. So F bar is equal to integral dF bar, that is equal to integral I dl cross B bar. So integral dF value is equal to F bar, I is a constant. Now dl, by integration of dl, it becomes to L cross B. As we already know, A cross B value is AB sin theta. In the similar manner, L cross B is equal to LB sin theta. So simply, the magnetic force experienced by a current carrying element placed in a magnetic field is F is equal to BIL sin theta, or simply Bill sin theta. Now the next concept is the force experienced between two parallel infinite long current carrying conductors. So here, so these are the current carrying conductors. Here, this is Q and this is S. They are long current carrying conductors. So the I1 is current passed through Q conductor and I2 is the current passed through S conductor. Now, here, whenever a wire carrying conductor, that means a current carrying conductor produces a magnetic field. So when you observe this figure, the impact of current passed through Q on S. The similar manner, the current passed through the conductor S impact on Q. So a magnetic field on RS due to current in PQ is expressed as, that means here the B1 magnetic field is developed due to this PQ conductor. Now it is at a distance R. As we already discussed in Biot-Savart's law, the current carrying conductor, that means the magnetic field developed due to a current carrying conductor, is expressed as B is equal to mu naught I1 by 2 pi R. Here, this is the magnetic field at RS conductor due to PQ conductor. So that's why here we have to write the I1 value here, and R is the distance between the where we have to find the magnetic field to a line, that is small r. So now the force acting on RS. So the force acting on RS due to I2 through it is expressed as F21 is equal to mu naught I1 by 2 pi R I2 L sin 90. So this is the expression of force acting on RS due to current I2 through it is. So simply the F21 is expressed as mu naught I1 I2 L. Here the sin 90 value is 1, which is equal to 2 pi R. So here B1 acts perpendicular and into the plane of the diagram. According to right hand thumb rule, the angle between I and B1 is 90 degrees. So the L is the length of the conductor. Then this is the expression for the F21, mu naught I1 I2 L by 2 pi R. Similarly, force acting on PQ due to I1 is expressed as F12 is equal to mu naught I1 I2 L by 2 pi R. When you observe that the force acting on the both conductors are equal, that means the force per unit length of the conductor is simply by cross multiplying the L here, that is F by L. So F is the force, L is the length. Then the force per unit length of the conductor is expressed as mu naught I1 I2 by 2 pi R, Newton per meter. So here there are two cases. The first one is the current passed through these two conductors are in a same direction. Then, according to Fleming's left-hand rule, the conductors experience force towards to each other and hence they or attract each other. And the second case is the current passed through the conductors in a opposite manner. According to Fleming's left-hand rule, the forces are move away from each other. That means they are repelled to each other. And next, definition of ampere. Force per unit length of the conductor. That is the force per unit length. Already we discussed in that. F by L is equal to mu naught I1 I2 by 2 pi R. Let us assume I1 and I2 values are 1 ampere and the distance between the two conductors is taken as 1 meter. Then by substituting here, the force per unit length value is equivalent to 2 into 10 power minus 7 Newton per meter. Now, the definition of ampere is taken as 1 ampere is the current which, if passed in each of two parallel conductors of infinite length and placed 1 meter apart in vacuum causes each conductor to experience a force of 2 into 10 power minus 7 Newton per meter of length of the conductor. Now, the representation of magnetic field in these two cases. This is the first case. As you observe the figure, whenever the directions of the current on both conductors are in the same, then this is the magnetic field. So here, this is a north pole. So here you observe that the direction of I1 and the direction of I2, the field developed due to I1 and I2 are in an opposite manner. That's why there is an attraction between them. Whenever the charges are, that means the conductors inside the conductors, the current flow in opposite direction, then you observe that the magnetic field directions in both are in a same. That's why here there is a repulsion takes place. So this is the representation of a magnetic field developed due to parallel current when they are in the same direction and in opposite direction. And next we discuss about the basic definitions of what is a dipole, what is a bar magnet and dipole momentum. So as we already know in our lower section, once again I discuss about what is a bar magnet. So the line joining the poles here, the south and the north, the line joining the poles of the magnet is called a magnetic axis. The distance between the two poles is called magnetic length of the magnet. And the distance between the ends of the magnet is called, that means not a poles. When you observe that ends of the magnet, that means when you observe the figure, here the pole strength is just in front of the ends. So the length, the distance between ends of the magnet is called geomagnetic material length of the magnet. The ratio of the magnetic length and geometrical length is equivalent to 0.84. Now, magnetic dipole. So, what is a magnetic dipole? A pair of magnetic poles of equal and opposite strengths are separated by a finite distance is called magnetic dipole. So here, the magnetic dipole is represented by capital M. Now, the magnitude of dipole momentum is simply a product of pole strength M and the separation between the poles, that is 2L. So the magnetic momentum capital M is equal to small m into 2L. So here the one cap means it is a unit vector. The SI unit of magnetic dipole momentum is ampere meter. So the direction of dipole momentum is always from south pole to north pole. Actually, outside the magnet, the direction of the magnetic field is always from north to south. But in case of dipole momentum, the direction is from south pole to north pole. Now the next topic is torque experienced by a current loop in a uniform magnetic field. So when you observe the figure, this is the magnetic field direction and it is the current loop that is in a rectangular shape. P, Q, R, S, P. Now the width of the rectangular, that is current loop, is taken as a B and the length is a small l. Now, whenever a current loop, that means a current carrying loop, is placed in a magnetic field, as we discuss in according to Lorentz magnetic force, automatically it starts rotation. So due to that, a torque is acting on the dipole. So the torque of the current loop in a uniform magnetic field is expressed as, let us discuss that. Theta be the angle between the plane of the loop and the direction of the magnetic field. So when you observe that, so here it is the theta. So this is the loop. So the angle between the loop and to the magnetic field, according to magnetic force, F is equal to I B cross B. Here the I is current and B is the width of the rectangular loop. So B cross B is taken as BB sin theta. So here we have to take in the current loop into two parts. One is along SP direction. When you observe that, this is SP direction. So this SP direction length is taken as a B. Now the force experienced by this SP direction is represented as IB capital B sin theta. In the similar manner, the force on QR is also equivalent, which is equal to IB capital B sin theta. Now, the forces on SP length and QR are equal in magnitude, but they are in opposite direction. Due to that, they cancel to each other. And moreover, they act along the same line of the action. That means axios, and hence the dot product between hence do not produce a torque. Now, the side PQ. So here, the side PQ magnetic force is equivalent to I into L cross B. So here L is the length of that side. So similarly, ILB sine 90 degrees. Why here we have to take it as a 90 degrees? The angle between the loop side, this is the loop side, and to the magnetic field, when you observe that 90 degrees here, this is the side and this is the magnetic field. The angle between PQ side and to the magnetic field is 90. So on PQ side, there exists a maximum force. So that is 90, which is equal to ILB. In a similar manner, on RS side also equivalent to IL cross B, which is equal to ILB sine 90 degrees. Sine 90 value is 1. So ILB. So by observing these two values, that means the force experienced by the side PQ and RS are in equal in magnitude, but they are in opposite direction, cancel to each other and do not produce any translation motion. But they act along in different lines of action. Hence, they produce a torque about the axis of the coil. That means they cannot produce any translation motion, but they act on a different, they act about the axis. So that's why they produce a torque about the axis of the coil. So torque experienced by the coil, as we already basic definition, torque T is equal to force into displacement. Here the force on PQ side is FPQ and the displacement is along P and direction. So the force is ILB and the Pn value by calculating the triangular, this is equal to B cos theta. So the torque is ILB capital B cos theta. Here the length into breadth is equivalent to area of the rectangular. So by replacing LB value as a So that is I into A. Now, torque T is equal to NIAB cos theta. Here capital N is the number of turns on the rectangular coil. If phi is the angle between the normal to the coil and the direction of the magnetic field, then theta plus the phi value is equal to 90 degrees. So that means theta and phi are complementary angles. So torque T is equal to IAB cos of 90 minus phi. Cos 90 minus phi is equal to sin phi. So torque T is equal to NIAB sin phi. So here cos and sin are depends on the angle taken, whether with the plane of the coil or the normal of the coil. Now the torque in a vector form we can write as NI A cross B. That means here N and I into A. That means magnetic dipole momentum. The expression of current I we can also written as in terms of magnetic momentum also. So magnetic momentum M is equal to I into A. So this is the torque acting on a rectangular loop. Now the important note on this concept is the coil will rotate in the anticlockwise direction about the axis of the coil. That is as shown in the dotted lines in the figure. Now the torque acts on the upward direction along the dotted line. If theta is equal to 0, then torque is equal to 0. As substitute the phi value 0, then sin 0 value 0, automatically the torque value becomes to 0. If phi is 90, then we get a maximum torque on it. So that value is equal to NIAB. Now the units of torque is expressed as a Newton meter. Why? Because B in Tesla and current in ampere and area in meter square. Now by substituting these all units, we get the torque units as a Newton meter. The above formula for torque can be used to calculate the loop irrespective of the shape. So these are the key points we have to know about the torque acting on a loop placed in a magnetic field. So next class we discuss about the solved problems on this magnetic force. So these are the topics: torque acting on the current carrying loop placed in a magnetic field.